So today we're in a new section. We're talking about similarity and diagonalization. So they're intertwined, connected, because our main goal here is to diagonalize a vector, whatever that means. But the idea behind this is that we are looking at an application of the eigenvalues and eigenvectors that we've been talking about. Now, there's a lot of applications that exist, but this is the first one that we're going to discuss, and this one is not nice and easy and mathematical, and I think it's simple enough to be able to jump on. And then after we're able to do this diagonalization, we'll apply it to doing things like raising the matrix to some unknown power or whatever. So here's a definition to begin with. Let's take a look at similarities. If you have two matrices, and they should be square matrices, we say that they're similar if there exists an invertible matrix such that you can multiply the first matrix on the left and the right by A in its inverse, or P in its inverse, and then you should get the B matrix. So this is generally how similar matrices are defined, but sometimes if we take a matrix, or we take that P, you take this equation over here, P inverse A P is equal to B, and then you multiply both sides on the left side by P, then we'll see that you have some canceling going on, and you have AP is equal to P times B. So sometimes another way to define similarity is with this equation instead of this equation. But the nice thing about this first equation, or the equation that's included here, is that it's understood that the inverse does exist, and P has to be invertible. So that's interesting, I guess. And if we continue talking about this idea of similar, it looks like A is similar to B is a one-way idea, but it turns out that this similar is like an equal, except it's not equal, right? But it's similar to an equal. What? Similar is similar to saying equal. What I mean by that is that with equality, do you guys remember reflexive, symmetric, and transitive properties of equality? Sort of. Well, the next theorem shows this idea that being similar has these properties. It's like congruent or something like that. So this is just more theoretical stuff. We have this A is similar to A is saying that similarity is reflective. We're saying if A is similar to B, then B is similar to A, and that's symmetric. And then if A is similar to B and B is similar to C, then it should follow that A is similar to C. That is transitive. So these are like the properties of equality. And I don't know if you guys remember working through something like this in geometry or something where you have to prove things. But this just shows that saying that something is similar to another, it's not the same as saying it's equal, but it's kind of the same, similar. I know that's not a good word to use, but let's prove one of these, just because these proofs are fairly easy to do. I was going to do symmetric, but I think transitive is just a tad bit more interesting, and so maybe I'll have you guys do this on the test where you have to prove symmetric or something. But I'll prove transitivity. And so we want to assume that A is similar to B and B is similar to C. So we assume this. Assume A is similar to B. And if A is similar to B, then that means that there exists the P matrix. There is P such that by definition, A similar to B means you wrap these other matrices around A. So P inverse AP is equal to B. And then you also assume that B is similar to C, then that means there exists, and I can't use P again because I had already used P, so let me use another letter. What comes after P in the alphabet? Q? P, Q? Q such that Q inverse B, this time B is the first one, right? Q inverse B, Q is equal to C. That's the second matrix. So now I want to show that A is similar to B. Or no, I want to show that A is similar to C. That's my conclusion part. So to show that, want to show A is similar to C. So let me put this in like parenthetical statement. So to show that, I can say that A is similar to B, and then B is similar to C. So I'll say A, how should we do this? P inverse P, this is equal to B, right? But then if I wrap this around with a Q, Q inverse P inverse A, P, Q. So what I did was I took that first equation, the similarity between A and B equation, and then I multiplied it by Q inverse on the left and Q inverse on the right. What should I get? According to our second assumption, that Q inverse B and Q is equal to C. So if I just, matrix multiplication is associative, so I can regroup this first expression over here. So if I regroup this first expression, I have Q inverse P inverse grouped together, A and then PQ grouped together is equal to C. And now I'm not quite done yet. I just have one more step, and that is to realize that the inverse, that the product of an inverse is the inverse of the product. Wait, the inverse of a product is the product of the inverses written in the opposite way. So I can rewrite this as PQ inverse A PQ is equal to C. So now I've written this relationship between A and C where A is similar to C. So if we just say one more thing, where PQ now is, as a product, is invertible, then we've essentially written the criteria for A being similar to C. And so A is similar to C, and then we're done. Okay? So that's just a quick proof. I think the symmetric is slightly easier, and you'll see it's just a matter of understanding the idea of an inverse. Reflective should be easy too. Okay, so that's the proof for C, and I think the book has proofs for A and B as well. I don't know. Maybe they proved everything, but it's the idea is coming up with an equation where the first matrix is multiplied on the left and the right by some inverse and the original some P matrix. All right, I think there's one more theorem about inverses or about similar stuff. So here's another theorem with a little note at the end. So if we're assuming that A and B are similar, then the following are going to hold. The determinant of A is the same as the determinant of B, and then invertibility works if one has an inverse, then the other one is also going to have an inverse. A and B have the same rank, they have the same characteristic polynomial, and then this one over here I think is really important. They have the same eigenvalues. So similar matrices have the same eigenvalues. Now, it's important that this theorem first assumes that A is similar to B. This is your assumption. Your assumption is that A is similar to B. This is assumed. And if you say that A is similar to B, then everything else will follow. Now, this is not what they call an if and only if statement. It doesn't mean that we can go backwards. Remember there was this long list of things where you say everything is equivalent, and if one is true, then everything else is true. So in this case, it doesn't go backwards. So for example, two matrices may have properties A through E in common and yet still not be similar. For example, if you have the determinant of A equal to the determinant of B, that doesn't mean that those matrices are similar. And they have an example in the book that I'm going to use also. What's that example? So this is an example that they give, just really quick. Whoa. So determinant of A, remember how to find determinant of 2 by 2 matrices? It's product of the diagonals minus the product of the wings. So this is 1 minus 0. And determinant of B is also 1. So the determinant of A is equal to determinant of B, but it turns out that these two are not similar to each other. But A is not similar to B in this example. How can we show that? How can we show if two things are similar? You have to find a P, right? So A is not similar to B. I just put that slash over there to say it's not similar. That's because if you have P inverse A P, I don't know what P inverse is yet. We'll figure that out. But A is, what's A? If you look at A, can you see what A is? A is just the identity matrix, right? So if this is an identity matrix and you regroup this a certain way, it doesn't matter, it doesn't really matter what P is equal to, right? You could just, this is the same thing as P inverse times P. What's P inverse times P? That's the identity matrix again. And clearly this is not equal to B, which is not the identity matrix. So if you know that two things are similar, then you can conclude all these other things about the matrices. But if one of these things is true, it doesn't imply that those two matrices are similar. So that's our little note here, be careful. Yeah?
So we determine if two matrices are similar just looking at numbers?
I don't think so. I think there's a little bit of work to show that something's similar to another. Okay, let's get to what we actually want out of these similar matrices. What do we want out of them? The idea that a matrix is diagonalizable. So let's get this definition down in our notes. So a square matrix A is diagonalizable if you can find a diagonal matrix such that A is similar to that diagonal matrix. Okay? So whatever A might look like, if we can get P inverse P is equal to some matrix that has a diagonal and zeros everywhere else. So if we can find P so that this ends up to be a diagonal matrix, then we can say that A is diagonalizable. All right? So we can think about why this is important or why this might be useful. But before we do that, let's think about what do you think is going to be in the diagonals? Those numbers in the diagonals must be important, right? Must be important. What do you think they would be if we're able to diagonalize a matrix? What do you think those stars are? What can we say about the diagonal? Can they be non-zeros? Can they be 0? I think they probably could be 0. They're the eigenvalues. So you could have a 0 as an eigenvalue, and if you do have a 0 as an eigenvalue, that just means your matrix A is not invertible, right? If you have a 0 for an eigenvalue, then your matrix won't be invertible. And but that's okay for similar matrices. All right, let's before we continue talking about it, let's go back to that theorem over here. It says if you can find this A similar to B, and pretend that B is the diagonal now. So suppose B is your diagonal matrix. Then the determinant of A is equal to, let's just skip down to this last one. They have the same eigenvalues. So remember, if you have an upper triangular matrix, what are the eigenvalues? The diagonal, the product of the, not the product, but the diagonals themselves, those are the eigenvalues. So from the last theorem, if you're able to write your A as being similar to a diagonal matrix, then that diagonal will be made up of diagonal of eigenvalues. Now, if it turns out that one of those eigenvalues are 0, that just means that this diagonal matrix is not invertible, and that would imply that A is also not invertible, and that's okay. Because they have the same rank. Oh, A is invertible if and only if B is invertible. So if B is not invertible, then A is also not invertible. So it's okay to have 0 as an eigenvalue. It's okay to have 0 as one of those diagonal values. So because similar matrices have the same eigenvalues, then it's going to be necessary that these diagonal values are actually the eigenvalues of A. Okay? So that's an important piece of information that we could take with us. Let's take a look at the next theorem over here. I think this is the one that's going to allow us to find our diagonalization. Let me put this, sorry. Let me put this over here. Okay, this is a theorem in the book that says if A is diagonalizable, you can diagonalize A if and only if it has n linearly independent eigenvectors. So the P, it turns out that the P has to be invertible. A itself doesn't necessarily have to be invertible, but P, since you're taking P inverse, it has to be invertible. So more precisely, there exists an invertible matrix P and a diagonal D such that this is true, and if and only if the columns or P are linearly independent eigenvectors of A. So this is your key to finding your diagonalizable matrices. We know that the diagonals are going to be made up of the eigenvectors, or eigenvalues, sorry. The diagonals are going to be made up of the eigenvalues. And then now for each of these eigenvalues, we have a corresponding eigenvector. We would write your matrix P made up of columns of those eigenvectors. Does that make sense? No. No. Okay. So I think when we do an example, it'll make a little bit more sense. But all last week, we've been looking for eigenvalues and eigenvectors and stuff. So we would find an eigenvalues, and then we would find the corresponding eigenvectors and talk about the eigenspace. But now we have something else to do with those eigenvectors, and those eigenvectors are gonna make up our invertible matrix P. So how should we write this? Oh, let's just do an example. Let's do maybe number 9 or something, and then we'll do a 3x3, and we'll do one of these with a K. I seem to like those types of problems with Ks in it, and quizzes and exams and stuff. So we'll try to do one of those. Which one we're going to do? 9? Let's do number 9. So the idea is to see if we can find the not the eigenvalues, but see if this is diagonalizable. See if we can diagonalize this matrix. First, let's see if we can find the eigenvalues. So let's find the eigenvalues, e-values. And how do we do that again? We subtract something. Remember? Lambda. Lambda times identity, right? So we do a little a minus lambda I business, and then make a characteristic polynomial out of that. All right, so let's see. The determinant of a minus lambda I, I'm going to set that equal to 0, is going to be negative 3 minus lambda 4. Remember, the wings don't have, we're not subtracting anything, right? And then we have a 1 minus lambda. And we want to find the determinant of that, and that's how we can construct our characteristic polynomial. So we got minus 3 minus lambda times 1 minus lambda. So the determinant of 2 by 2 is easy. It's just the product of the diagonals minus the wings. So the product of the wings is negative 4. And then we should FOIL it out and do all kinds of other stuff. So we got minus 3, got minus, no, it becomes a positive, right? So positive 3 minus 1. So negative 3 minus 1, negative 2, negative 2 lambda, and lambda. Oh, okay, so it's positive. Okay, good. And then we have a plus 4 towards the end there. We want to set this equal to 0. Let me first rewrite it in the nice quadratic equation-y looking thing. And this would be a plus 1, the constant, is equal to 0. Can we factor this? So we can if you can't factor, then you have to go through the quadratic formula business. So this is factorable. We got plus 1 squared. So we have an eigenvalue, lambda is equal to 1, that has multiplicity, algebraic multiplicity, negative 1. So lambda equals negative 1 with algebraic multiplicity of 2. Okay. So let's find eigenvector. So by the way, your D, now that we have the eigenvalues, you have your D already. And because this has algebraic multiplicity of 2, we write it twice. And so this is your diagonal matrix. So let's find the eigenvectors for lambda is equal to -1. And hopefully we come up with 2 of them. I don't know if we're going to come up with 2 of them. So with lambda is equal to 1 or lambda is equal to -1, we come up with, rewrite this equation over here and rewrite this vector or this matrix. -3 minus -1, that's your lambda. 4, -1, and then 1 minus -1. So your matrix turns out to be -2, 4, -1, and +2. And then if you row reduce, you'll see that you'll be able to get rid of one whole denominator thing, right? So I think if I multiply by -1/2, this will be 0, -1/2, -2. That's equal to 0 also. We should expect that because we should find a null space. And here, we're only going to have one eigenvector, I think. So -2x plus 4y is equal to 0. Oh, by the way, we're going to let y equal to your free variable. So -2x is equal to -4y divided by -2. X is equal to 2y, or you can just call it t. So then your solution, xy, is equal to t times x has a 2 and y has a 1. So what's your geometric multiplicity here? So unfortunately, this is only a one-dimensional subspace. And so this is geometric multiplicity. And so your P matrix that you were looking for is 2, 1, 0, 0, which is not invertible. So unfortunately, A, your matrix A, is not diagonalizable. That's a bummer. Should have had one that was actually diagonalizable so that we can see it. But in this case, it's not diagonalizable because we only have one eigenvector for that. Generally, this is what you would do. You would build your matrix P with the eigenvectors. All right, well, let's try another problem. See if we can find one that actually is diagonalizable. 12, maybe, or 13. If we found another eigenvector, yeah, we have -1 and -1, so it's the same value. All right, so it's not diagonalizable. Let's take a look at another problem here, number 12 or 13. Let's do number 12. Hopefully this one will work. Hopefully this is diagonalizable. If nothing else, we're getting practice in finding eigenvalues and eigenvectors, right? All right, let's find the eigenvalues. E values. So we need a minus lambda I and the determinant of that. So we got 1 minus lambda, 0, 0, 1, 1 minus lambda, 3, 3, 0, and another 1 minus lambda. This is not looking promising. Oh, let's see. We got 1 minus lambda times 1 minus lambda times 1 minus lambda. Oh, wait. We're finding the determinant, right? So I would expand maybe on the first row. Seems sensible. We got zeros and stuff. So it'll be 1 minus lambda times 1 minus lambda, 3, 0, 1 minus lambda. Minus 0 plus 0 in terms of expanding. And then it looks like the determinant is 1 minus lambda. Oh, this is not good either. Yeah. Well, but then that means your eigenvalues are 1 3 times, right? Let me see if I get 3 non-zero eigenvectors before we go on. So A equals 1, 0, 0, 1, 1, 3, 3, 0, 1. Eigenvectors. Yeah, I only get 1 eigenvector. All right. Sorry. What? Yeah. Let's see if 13 will work. One, negative 1, 0, 1, 1, 1, 0. Nope, that one doesn't work either. Number 10. Wow. Number 11. Ooh, number 11 works. All right, well, let's try number 11. So let's find the eigenvalues first. A minus lambda I, 1 minus lambda, 0, 1, 0, 1 minus lambda, 1, 1, 1, 0 minus lambda. So in terms of expanding to try to find a determinant, I guess first row or the first column has zeros. Let's expand the first row. So I have 1 minus lambda times the determinant of the submatrix, 1 minus lambda, 1, 1 minus lambda, minus 0 plus 1 times the determinant that's left over if you cross out on the first row, third column. 0, 1 minus lambda, 1, and 1. All right, so let's find the determinant of this first submatrix. 1 minus lambda times the determinant is 1 minus lambda times negative lambda minus 1 times 1. And then this one is 0 minus 1 minus lambda. All right, let's do some multiplying. Negative lambda, positive lambda squared, minus 1, plus negative 1 plus lambda. Am I doing that right so far? How's your algebra? All right, let's attempt to multiply this. I'm going to multiply this in some particular order. Negative lambda plus lambda squared minus 1. And then the next one, let me get rid of the parentheses and see if I can do this without the parentheses. So negative is positive, lambda squared, negative lambda cubed, positive lambda, and then minus 1 plus lambda. Boy. All right, collecting terms, I got negative lambda cubed. I have a cubic polynomial to deal with, so I'll take all the squares. There's 2 of them. Positive 2 lambda squared. And then I'll take the linear terms. So that's just minus lambda. And then I'll take the rest of the constant terms. Negative 1, that's negative 2. Plus 2? Plus lambda. Okay. So this is a third degree polynomial with 4 terms. So hopefully we can factor by grouping. You remember doing that back in the day? Whenever that was. Maybe I'll take out a negative lambda squared for the first one. Or for the first 2, that is. So I'm going to factor from here. Negative lambda squared. This becomes a lambda negative taken out, minus 2. and then I have just a lambda minus 2. I'll put that in parentheses and pretend that there's a 1 in front of it, and I can factor that out. So lambda minus 2 factored out, I'm going to get negative lambda squared plus 1. And negative lambda squared plus 1 is 1 minus lambda squared. So I have 3 eigenvalues. That's great. So lambda is equal to, let's put them in order negative 1, positive 1, positive 2. Okay. So it looks like we have 3 eigenvalues, and if each of them will have their own eigenvector, then we're in good shape to make this diagonalizable. Any questions so far? All right, let's write our diagonal matrix now, and then we'll come back to it a little bit later. May need to copy it onto the next page, but your diagonal matrix is going to be negative 1, 1, and 2. So the order of this doesn't really matter, but your P matrix that we'll find will depend on the way you have this ordered. For now, let's just leave it at that. Okay, so the next part is for each of these eigenvalues, we want to find their own eigenvectors. So eigenvectors, let's start off with lambda is equal to minus 1. So lambda is equal to minus 1. So we're going to essentially recreate this matrix A minus lambda I, and then we're going to try to find the null space of this. Right, that's how we find eigenvectors. So I'm just going to go ahead and put lambda here in this matrix. Lambda is equal to negative 1. So 1 minus negative 1 is 2. 0, 1. 1 minus negative 1 is 2 again. And then 1, 1, and then negative, negative, and this is positive. So I think I should be able to get rid of the bottom row with a couple of row reducing steps. Let's see. If I take the first row, multiply it by a half, negative a half. Negative a half, row 1, add it to row 3. I'm going to get 0. 1, multiply this by negative 1/2, add it to positive 1, it becomes positive 1/2. Now I'll take row 2, multiply that by negative 1/2, add it to row 3. 2, 0, 1, 0, 2, 1. And then 0, this will become 0. And then this is negative 1/2 added to positive 1/2 at 0, which is what we would expect, which means we got a free variable for z. And then we have 2y plus t is equal to 0. So y is equal to negative 1/2 t. And then I think that's going to be the same for z, or for x. 2x plus t is equal to 0. So x is equal to negative 1/2 t again. So your solution for this null space is going to be the one-dimensional vector space spanned by negative 1/2, negative 1/2, and 1. So if you don't like fractions, since this is a vector that's going to span something, you can have any scalar multiple of this. So you can rewrite this as another variable t, which we can put s or t prime or something, t star, whatever. And let's take out we could even take out a negative if we want. We can take out a negative 2 or negative 1/2. So this becomes 1, 1, negative 2, or something that's a linear or a scalar multiple of that. So that could be 1. That's the eigen vector for the eigenvalue negative 1. Let me put a box around here. Okay, so that's the first one. We got 2 more to go here. Let's say lambda is equal to 1. That's our next eigenvalue. So we put 1 in for lambda. We're going to get 0, 0, 1, 0, 0, 1, 1, 1, negative 1. So I think with a row switch and knocking off one of these 1s, we should get our reduced matrix. So I'm going to switch the first row and the third row, and then since this is exactly the same, I can just subtract and get that 0. So here it looks like z is going to be equal to 0, right? From this equation, z is equal to 0. So it looks like your y is going to be your free variable, and then you have x plus your free variable y minus your z, which is equal to 0, is equal to 0. That's the first line, the first row over there. We're going to get x is equal to negative t. That means your x, y, z is equal to t times negative 1, positive 1, and 0. So that's your eigenvector corresponding to your eigenvalue 1. All right, let's do one more. Your last eigenvalue is positive 2. Let's see how this is going to look like in terms of this matrix. 1 minus 2 is negative 1. 1 minus 2 is negative 1 again. And we got 1, 1, and then negative 2. So I think this is very similar to the first one that we had. We do a couple of row operations to get rid of the hole down there. So let's just pretend that we did that. And we're not going to get rid of the first or second rows, but we can get rid of the third row by adding the first row to it and adding the second row to it. And then eventually it'll disappear. So this is what we have. And then we can assign z as the free variable. And then we have negative y plus your free variable is equal to 0, which means y is equal to negative t, positive t, positive t. And then your x, negative x plus t is equal to 0, so x is again going to be positive t. So then eigenvector for this would be, let's see, 1 for x, 1 for y, and 1 for z. And so hopefully these three vectors are all linearly independent from each other. Are they? Yeah, they are. So I'm looking at these three vectors that I circled. And if we put them in the order of the eigenvalues in the diagonal, you can have your P vector or your P matrix as, so for negative 1, it's 1, 1, negative 2. For 1, your eigenvalue 1, we get negative 1, 1, 0. And for your eigenvalue of 2, we get 1, 1, 1. And so if this actually did work out correctly, we should be able to find the inverse of P and then multiply it with A, and then we should get the diagonal. So we're going to attempt to do that next. Okay. Let's see. Let's take these two. Should we do the inverse by hand? I don't know exactly yet. Let's copy A as well. All right, let's find the inverse. Should we find? Really just tempted to type it. Do you guys need practice on getting the inverse by hand? What? Yeah. Maybe we should practice finding the inverse. All right, let's see if we can find the inverse. Let's take our P. 1, negative 1, 1, 1, 1, 1, negative 2, 0, 1. And let's throw the identity next to it and then do this a bunch of row reducing steps to make this left-hand side into an identity matrix. And let's take a couple steps at a time. So for this first one, I'm going to multiply the first one by negative 1 and add it to row 2. So 1, negative 1, 1, 1, 0, 0. So adding that to row 2, negative. So this becomes negative. This becomes negative, negative is a positive. Add it and it becomes 2. This becomes 0. So we add negative 1. All right, let's do another step here for the third row as well. So let's multiply the first row by 2 and then add it to row 3. Replace row 3 with that, we get 0. So this becomes negative 2. Right? This becomes 3. And so 0, 2, 1. Okay so far? You do it right? All right, good. All right, now let's get rid of this negative 2 by taking just adding row 2 to row 3. Oh, so row 1, yeah, so this should be a 2. Yep, thank you. Thanks for catching that. All right, now let's add row 2 to row 3. We get 1, negative 1, 1, 1, 0, 0. First row doesn't change. Second row won't change either. So now this is the one that's going to change. So adding that, this remains a 3. Adding row 2 to row 3, we get positive 1, 1, and 1. All right. So this is in row echelon form. It's not reduced yet. So let's do a couple of things to reduce, make this into a reduced row echelon form. And we can wipe out not wipe it out, but make these into 1. So multiply R2, multiply row 2 by a half, and multiply row 3 by a third. So this becomes 0, 1, 0, and everything else gets multiplied by a half, so negative a half, positive 1 half, and 0. And here we got this to be 1. Everything here is a third. All right, a couple more steps to fix up the first row. We have we can multiply the third row by negative 1 and add it to the first row. Replace the first row. So everything else should remain the same. So the first two doesn't change. And then this last one becomes 0. wait. The last one becomes 0. Right? So I added, I take the third row and I multiply it by -1 and add it to the first row. So the third row multiplied by -1 is -1/3. Add 1, that's positive 2/3. -1/3, -1/3. And then one more, we take the second row and add it to the first row. So R2 plus R1, replace R1. So I'll take the second row and add it to the first row. This will give you a 0 over here. Take the second row, add it to the first row. I got 2/3 minus 1/2. That's 4/6 minus 3/6. 1/6. 1/6. 1/2 minus. So this is a -1/6. This is a -1/3, right? So it should be positive. And then this one, does this one change? No. All right, that's the inverse. So the inverse is 1/6 1/6 1/6 -1/3 -1/2 1/2 0 1/3 1/3 1/3. That's nice. So the idea is that if you were to multiply P inverse A and P, you should get this diagonal D. I don't know if I want to do that. So let me just punch it in the calculator and see. So your P vector, our P vector we got to be 1 minus 1, 1. One, 1, 1. Minus 2, 0, 1. Let's see. See if we did the inverse correctly. Look right? Wow. Does look right. That's impressive. All right, let's multiply. So P inverse multiplied with A multiplied with P is our diagonal. -1, +1, and 2. So it did work out. We can just say that we multiplied it in Mathematica. Okay. Well, that was finding the inverse was just took longer than I thought. All right, let's squeeze in a couple more theorems here. I think that's the bulk of this particular section. Is I want you to be able to find whether something's diagonalizable, and find the P and the D matrices. But here are a couple of other theorems to throw at you. We have one theorem that talks about the basis for the eigenspace. So A is an n by n matrix. Let lambda 1 through lambda k be the eigenvalues. Now some of those eigenvalues, they have k and n here, so k could possibly be less than n. And if k was less than n, you have less eigenvalues than the dimension of your matrix, which means one or more have multiplicity bigger than 1. So if B sub I is a basis for the eigenspace, remember how we find the eigenvectors? So they span our eigenspace. Then the collection of all those basis vectors is linearly independent. So we found these vectors over here. These vectors that are circled in purple. We found these 3 vectors, and before we put them into that matrix P, I said we should probably check whether they're linearly independent or not, right? Because if they're linearly dependent, then your P matrix won't be invertible anymore. Remember, if that's one of the rules, if you have your columns are linearly independent, then your matrix is invertible. So if it's not linearly independent, then it's not going to be invertible, which means it's not diagonalizable. So that's what that theorem is saying, is that all those vectors, all those eigenvectors that you would find for the collection of all the eigenvalues, all put together, are going to be linearly independent. Okay, so that's one theorem. The next theorem says that it's going to be diagonalizable if you're going to find exactly n eigenvalues. Let me say it backwards. If you have n eigenvalues, distinct eigenvalues, then it's diagonalizable. Okay, that's the case that we just saw. So yeah. Not necessarily. No, it still could be diagonalizable if, as long as you have the same multiplicity as the geometric and algebraic are the same multiplicity. All right. So the next lemma and theorem is the big theorem for this. So I'll put the lemma up here, and then we'll just have the theorem next time. So the lemma just says the geometric multiplicity is less than or equal to the algebraic multiplicity. So you can't have, if your algebraic multiplicity is 2, your geometric multiplicity could be 2, or it could also be 1. It could be less than that. But it can't be greater. You can't have an algebraic, you can't have your geometric multiplicity to be bigger than your algebraic multiplicity. All right? Okay, so that's it for now. You guys owe me a quiz, I think, right? So if you guys drop out that quiz on your way out, we'll be all good, and I'll see you guys on Wednesday.